Hi, my name's Anurag. I'm going to be talking to you on the deep dive about Amazon Aurora. You know, this is kind of an intimidating room from this direction, I've got to tell you. I feel like I should be singing, but don't worry, you're not going to see that. Good for both of us. So what I'll be talking about here is basically just the fundamentals of what is in Aurora and some of the recent improvements and some of the stuff that's coming soon. At least a few of those items were talked about in the keynote earlier today. So let's just jump into it. And I'll try to leave ample time for questions. I tend to go fast through these things. So Aurora is really a relational database reimagined for the cloud. And our goal here was to say that, hey, if we were really designing the relational database today as opposed to 40 years ago, what would we do? And how would we build it? And the answer ends up becoming somewhat different. And we really want to build something that has the speed and availability of a high-end commercial database, the simplicity and the cost-effectiveness of open source. No one actually wants a net new database, so we want to make ours compatible with MySQL and Postgres, the two most popular open source relational databases that are out there. And we want to provide all of the things you expect from a database from AWS, pay-as-you-go pricing, managed service, et cetera, et cetera. So relational databases came about a long time ago in the mainframe era, and you basically end up with this big blue box that's SQL transactions, caching, logging, and no matter what, if you look at most systems today, they continue to do that. And the difficulty that creates is that it has a large failure blast radius, right? It tends to be a scale-up architecture. There are systems that scale out, but not a ton of them. And even with those, the failure blast radius is quite real. And so one of the things that we do in Aurora is that we move storage, which is really what you care about from, state is what you care about from a blast radius perspective. We move that out into a purpose-built log structure distributed storage system. And the storage volume may be striped across hundreds of storage nodes. They're distributed across 3 availability zones. There's 6 copies of data, 2 copies in each AZ, and if any of these instances fail, we can certainly go and replace them quickly. They're stateless, so it doesn't much matter. The caching has been moved out of process, so if you have to do a restart of your database, let's say, because someone's running a query and this thing is hung, the cache will still be hot when it comes up, and so that also helps. So that's a slide I've used many times over the last 3 years. Here's a new one. So why are 6 copies necessary? So in the top picture, we're showing an example with a 2 out of 3 quorum, 2 out of 3 reads, 2 out of 3 writes, and basically your quorum is fine as long as you only have 1 failure at a time. And failures are reasonably rare. Let's say there's a 1 in 10,000 or 1 in 100,000 chance of a failure. To have 2 failures, if they're independent events, you multiply those numbers and it feels pretty rare. But the problem is, in a large fleet, there are always some failures that are going on, right? Disks fails, nodes fails, network paths fail. In a large enough fleet, there's always something that's broken and that needs to get repaired. Now, the problem is that AZ failures, availability zone failures, have shared fate. If you lose an AZ, you will have a quorum break on each and every quorum. And so the ones where you've got a red break up there, that breaks the quorum. And if that's a long-term destructive failure, you're lost. So we believe in Aurora that you need to tolerate AZ plus 1. So you can have 1 failure in the system at any given time, and if you lose an AZ, or you will end up basically being able to tolerate it from a read perspective. So in Aurora, we have 4 out of 6 quorum for writes, 3 out of 6 for reads. The quorum will survive an AZ failure. We've actually built a bunch of code to be able to tolerate even long-lasting failures. So for example, a couple of years ago, there was a snowstorm in Washington, D.C., and there were some concerns about the flat roof that happened to be on one of our data centers and whether it was going to survive that blizzard. And it did. Everything was fine, but if you lose a building in a long-term kind of way, which can happen, right? I mean, we all pay insurance for fire and so forth. That's because these events are possible, right? They're not impossible. Then that's a long-term failure. So in those cases, we drop down from 4 out of 6 to 3 out of 4 of the remaining nodes. And so if you have 3 AZs, that requires 6 copies. If you have 5 AZs, which not that many people do, then you can drop down to 3 out of 5 and still have AZ plus 1. If that makes sense. So why is that one failure okay? So that really turns into a question of how long does it take to repair. And we use 10 gigabyte segments. There's a 10 gigabit network. And so you can do the math on how long that repair takes from detection to repair. And so that really reduces your window of vulnerability, right? Because you're now talking about a handful of seconds in which time, in order to actually lose data, you need 2 of those to happen simultaneously, plus an AZ failure to lose 4 out of 6 and no longer have 3 out of 6 for repair. Or you need 4 independent events, and that's an awfully bad day, right? Now the nice thing about doing things where you have a high fault tolerance threshold is that you can use it not just for these catastrophic events, not just for the ongoing problems that occur in the large and the fleet, but you can also use this as a mechanism to just repair your system itself. Like, so for example, it's generally in most storage systems, it's a pretty big deal to patch it because you're injecting a failure. In Aurora, it's not. As long as I've make sure that I've got 6 colors for the various segments of something, then I can basically patch any one color at a time, and as long as the system's fine, right? Because I've injected a failure for a subset of the system, but that's fine. I can also use it to deal with heat management. So if I've got a hot node or a hot disk, I can just kill one of the segments on it, and it'll automatically get repopulated on some other disk on some other node. That's just how our repairs work. And that's cool, right? Because it takes what would normally be a complex, hard, challenging problem, and it makes it straightforward. One of the things I often talk about within my team is that latency is just a short-term version of availability, and availability is just a short-term version of durability, right? And if you have a system that properly deals with the performance and jitter and so forth using quorums, it also, the same exact model can be used for doing availability, the same exact model can be used for doing durability. So, just for any distributed systems geeks in the audience, I think that I would encourage you to think about that statement and how you might apply it in the systems you build. Another interesting thing that I think that's novel with Aurora, I'm not sure, is that you can do membership changes without stalls. One of the problems that would occur when I start doing all of these small segments, and I'm talking about failures happening, failures become more common. So I can't really manage changes to the membership in my quorum easily, right? In most systems, you're doing some things like a Paxos protocol to deal with a membership change. We don't. We use quorum sets. And so let's just walk through a failure of node F inside my quorum set that's A, B, C, D, E, F. And so what happens there is that I go from all nodes healthy to a quorum change, which is basically, hey, you can't write to this thing unless you're writing to the right quorum. And then if you're on the old version, you basically have to write to every member of it and say, update the epoch. And so you update the epoch, and then they're not going to accept a write unless somebody's got the right notion of the quorum set. So what we're doing here is that we're saying, okay, I want to go from A, B, C, D, E, F to A, B, C, D, E, G. And so I'm going to basically say that you need to write to a quorum set, which is A, B, C, D, E, F, and A, B, C, D, E, G. Now note that in this particular case, writing to A, B, C, D, which is a quorum 4 out of 6, actually satisfies that, right? And from that point, I can move forward and say, do a second epoch change and go to A, B, C, D, E, G, right? And remove A, B, C, D, E, F from my quorum set. And that works fine. the neat thing about this is that you don't have these funny edge conditions the way you do in these other membership change protocols, where you can't tolerate multiple changes, you can't tolerate writes and all of this. And during this entire process, I can continue to accept writes, accept reads, and accept additional failures, right? Like if after, while I'm in that second state, if E went down, I can just go and add H, and then I have just a more complex quorum set, right? And this is just Boolean math, right? And so, math is math, math works. And what's cool about this is that if you don't have a penalty for membership changes, then you can be aggressive about projecting a failure, right? So I can say like, hey, node F seems to be off. I'm going to claim it's down and start to bring G in. And I can just as easily go back to F if that was just jitter in the network, or go over to G, and that's fine, right? Both of those are perfectly legitimate cases to go to. And the quorum, the segment itself is small, so getting G in place is also an inexpensive operation. So, that's a little bit of new content that I haven't talked about before, but hopefully it's interesting. One of the other reasons that people tend not to use quorums is that they're great for writing. They kind of suck for reading, because you have to, read. If you're writing to 4, you have to read from 3 in the quorum set of in the quorum of 6. So we avoid that. Why? Because we can say like, I know who I wrote to and who act back to me, and as long as I know that this block is available on this node, why would I do anything other than just read from that node? So so the point is that most distributed systems abhor state. But in database systems are all about state. And so this is transient state. So in the case of a crash recovery, I may not have it, and I may have to reestablish all of this, and we'll talk about how to do that a little bit later. But from the perspective of an ongoing running system, I can cache which nodes are up to date. And even I can cache what the latency of each, the writes and the reads were from that node. So I can go and understand, sort of the storage weather, if you will, inside the system, because it's a multi-tenant system in the storage layer. And it doesn't have to be that I'm hot. Some other, caller to that node may be hot on some completely different activity on that disk. And so I might just go and, move to some other thing. So the read quorum is actually a repair quorum. The only time that I actually need 3 out of 6 is during a repair or a crash recovery, if I've, so unfortunate as to reach all of this. So I'm going to run through fast, and there'll be time for questions either at the end of this talk or afterwards. I can see a lot of confused faces. Let's move away from distributed systems and just talk about, why do we care, right? We care because it's faster, right? And so here's some numbers on Aurora compared to MySQL 5.6. Based on the Sysbench benchmark using the R416XL. I've shown a variant of the slide in the past. It used to show 500,000 writes, 500,000 reads per second, and 100,000 writes per second. What I mean by that is a DML operation or a select, not an IO. And the nice news here is that by going to a 16XL, we've doubled the write traffic, so we can run 200,000. The read is about the same on that node, and that's basically a packets per second limitation. If we were running local, we'd go higher. So how do we achieve this? At core, we achieve it because we do less work, and finally, at the end of the day, these databases are all about I/O. Networked systems, where you separated storage from compute. It's all about packets per second and network bandwidth and so on. So, it's really about reducing the IOs, minimizing the packets, processing asynchronously. And so what does that turn to? So let's compare RDS MySQL to Aurora in terms of the traffic. So there are 5 different types of writes that go on in MySQL. There's the redo log, there's the bin log, there's the data block. The data block actually gets written twice because it's not the same size as an atomic write to SSD, and you can end up in torn pages otherwise. And there are these abominations called FRM files, which represent the metadata state. And so let's say I was writing so I'm going to end up writing to an EBS volume. It's mirrored on the local side. Then let's say it's multi-AZ. So I'm going to go and process that over to a replica instance, and it's going to write step 4 and step 5. Now the problem with this is that step 1, 3, and 4 are sequential and synchronous. That means that all of the latency is additive. All of the jitter is additive. There are lots of different types of writes for any user operation, and the data blocks themselves, which are the largest portion of it, have to be written twice. So on the 30-minute suspense write-only workload, relatively small data set, with the largest number of PIOPS that were available at that time, we were able to run about 750,000 transactions, and which averaged out to about 7.4 IOs per transaction. Let's compare that to Aurora. So in Aurora, the only thing I write over the network is the redo log. And so I have to write it to more places, but the 6-copy amplification. But the redo logs are way smaller than data blocks, right? Like 100 to 1. And so what we have to do is we boxcar the redo log records together and ship them off using to the appropriate segments in a partial order, and then we issue the write. All of those steps are asynchronous, so we're doing asynchronous network processing. Interestingly, because the data pages are instantiated in the storage system, we don't have this notion of checkpoints or cache replacements, and that's a really big improvement, because the problem is that there's a positive correlation in the typical database between the activity that's happening in the foreground and the number of cache replacements and the amount of checkpointing that's going on. There's a negative correlation in Aurora. If you're really hitting the cache hard, you can just throw blocks away because they're getting instantiated in the storage node. So in this case, even though there's 6 times more log writes, there's 9 times less network traffic. And since it's all asynchronous, it's very tolerant, and it's quorumed. It's tolerant of network and storage outliers. So in this particular benchmark, we were able to run 35 times more transactions, and we were doing, despite the 6x amplification, 7.7 times less IOs. It's a big difference. So where did all those IOs go? So they went to the storage node. So what happens in the storage node is that we get a log record, we persist it onto a disk, and then we put into what we call an update queue, and we acknowledge it back. At that point, it's persistent, and we're done, as far as the head node's concerned, right? All the rest of the work is background. And so what we have to do after that is that we have to sort and group it. Since it was asynchronous, they might be appearing out of order. I may not have received one of those writes because it's a network, and networks have funny issues. And so we run a gossip protocol amongst the peers to make sure that we fill in all the holes. We coalesce those. That's basically redo, generating a new version of the data page. We write out of place. So you'll have the old version of the page and the new version of the page. That removes the need to do things like double write buffers. It does mean that we have to garbage collect in the background. And every so often, if we have space, we'll scrub them to make sure that our CRC checks are valid, and then we'll do backups of both the log and the data blocks to S3 before we can garbage collect. So the observations here is that all of these steps are asynchronous. Only steps 1 and 2 are in the foreground latency path. The input cube, dividing that prior number 7.7 by 6, because every storage node is only seeing 1/6 of the writes, right? The input queue is 46 times less than MySQL, right? And we're favoring the latency sensitive operations, and we're basically doing everything else in the background, which gives you this trade-off between latency and space. So if we're running out of space, we have to favor garbage collection and do standard queue processing to sort of put back pressure on the input queue. But if we're not, we can let it build up. And every workload has some amount of spikiness to it. And so this lets us smooth it out with background processing. The other big value that you get is that since we're doing the redo processing in the storage node, there's no crash recovery. I mean, there is crash recovery, but it's super fast, because normally what you have to do in a traditional database is that there's this classic 5-minute rule where by every 5 minutes you have to write all blocks that have been modified out to disk so that you minimize the amount of log processing that would be happening if you have to do a crash recovery. Now, one of the problems in MySQL is that that processing is single-threaded. And of course, your cache is cold. So even though it was 5 minutes in the foreground, that might have been happening across 100 threads, and was happening very likely across blocks that were hot in cache. Whereas here, so it might take an hour, right? I think we've all probably watched our databases take far longer than 5 minutes to come up. And even 5 minutes is a super long time to be out if you're running an internet site. So what we do in Aurora is that the underlying storage is replaying redo log records all the time. If you ask for a data page, either the page is current because we've done the coalescing, or we'll make it current by basically processing the redo log records from the last version of the page plus the log, just like any log-structured storage system. And so we just do that all the time as part of a disk read. And so we can also do that after a crash recovery. And the log application is, of course, parallel distributed asynchronous, but there's no replay for startup, and that ends up becoming a big deal. So let's look at what we have to do during a crash recovery. So let's say on an individual volume, we might have a bunch of writes that happen, a gap where something we've seen a write for entry 1000, but we haven't seen the write for some entry before it that was dependent upon. And so there may be some gaps and so forth. And so it's kind of what I call a ragged edge to the log. So there's this portion where everything has gotten 4 out of 6, and then there's some stuff that's in flight. The way other systems sort of deal with that is that they do two-phase commits. Two-phase commits take a long time, they're heavyweight, it's kind of sucky. So what we do instead is that we push, and rather than doing two-phase commits in foreground processing, we do the trimming of the ragged edge during crash recovery. So what we have to look for here is what's the consistency point? So actually first, what is the volume complete LSN? What is the LSN log sequence number, redo log record identifier, such that there are no gaps past that point? So you know that the volume is complete past that. So that's the point, that's the ragged edge. And so you're not actually interested in that point. You're interested in the last commit before that point, because anything that's not committed is gone, right? And so that's the consistency point LSN. So the last commit record, before the volume commit LSN. And so basically what we do after a crash recovery is we have to bring everything up, we have to compute these two numbers, and we have to trim those off from the log, and then we can start the database. And that's it. So it's basically some reads towards the tail of the log, opening all the volumes, et cetera. So that's a summary of sort of like basic Aurora. All of the stuff I described was true 3 years ago when we launched it. Let's look at some more recent improvements. So a few months ago, we launched fast database cloning. And an advanced database volume manager, say EMC or a NetApp filer or what have you, will basically do a copy on write clone of a volume. And so we do as well. And so what that means is you can clone the database without copying the data. And that, since you don't have to copy the state in the database, the creation of the clone is nearly instantaneous, certainly sub-minute. And what happens then is that I've created this clone volume, and as I write either on the original database or on the new database, we end up creating copies, right? And if we haven't done that, we can both read the shared data. So that saves both space, and it also saves time in terms of creating the copy. And this, I think, is going to be a really powerful feature for everyone, because think about the value of being able to clone a production database to run your tests, right? And so you've got some high fidelity data set, you can just run it and, or maybe you want to do a reorganization, like I want to see whether if I add this index and against the actual data and run the same workload against it, it is better or worse, right? Because I've added an index, so the inserts are going to be slower, but the queries are going to be faster. How do I trade that off? And it's much better to be able to do that against your actual data and your actual database, and to be able to create that index without impacting your production database, right? And you can do things like push a bin log from one database to the other to make sure that you get those updates going on. Sometimes you just want to save off a point-in-time snapshot and without impacting something. So someone says, I think there's something weird going on here. Well, let me, rather than shutting down activity, let it keep going forward, but I've got a copy of that system that I can use for forensic analysis, right? Let's briefly review how backup and restore works in Aurora. So what we do in Aurora is that we back up both the redo log and the data blocks. And as we reach a point of consistency where we can say all of the segments have all of the segments that comprise the data volume have reached at least this point, we can say that, okay, this snapshot has occurred to this point of truth, right? So everything's happening in background all the time, and what we're doing is we're just advancing the point in time when we can say, like, okay, this is the backup LSN, right? Very similar to the volume complete LSN I referred to earlier. So we're just continually streaming that stuff. And that's just part of the system. There's no such thing as like, okay, snapshot now, and then you suddenly get a burst of IOs happening in the system that interfere with foreground processing. And at restore, we just have to find the right stuff and pull it back down, both data blocks and redo log. And that also happens in parallel and synchronous. So that works. It works fine. It's a good deal faster than restoring a traditional database volume because it's happening so parallel. But normally the times when you're doing this operation are times that you're experiencing an outage, usually due to something like I dropped the wrong table or something like that, or I ran this insert statement or query, delete statement without the right where clause, not equal instead of equal. We've all done it. We've also introduced coming soon, and generally everything that says coming soon is like inside the next 3 months, right? Backtrack, which is, essentially near instantaneous restores. And what we're doing here is we're saying, we're not destructively writing data on disk, and we're garbage collecting it. If you said you wanted to keep an extra, a gigabyte of data, which represents an hour of log creation in your database volume, you should be able to pay for it and then be able to restore backwards in point in time, right? And be able to do that in the volume without needing to write anything, without needing to read anything. So this is just a metadata operation where we're just moving pointers around. And what we're doing is we're marking regions of the database, the log processing, as invisible. So we still walk them forward, we just don't apply them. And the nice thing about this model is that we also don't destructively overwrite when we're doing a backtrack. So if you say, I want to go back 15 minutes. No, gosh, that was wrong. Let me go back 13 minutes. Okay, wait, that was too far. How about 14 minutes? Okay, that's perfect, right? And that's just happening in the space, and it's like a jog dial. And so that works really pretty well. I think it's a feature that if you're running a production database, you pretty much should just have on. And I think it just adds a lot of value. A lot of what we're focusing on thus far in the talk is availability. You can see that. And it's just different angles to availability. And definitely one of the issues that can arise is user error, right? And so you want to be able to deal with those as well. Another thing that we added just a couple of weeks ago is auto-scaling of read replicas. And so basically, if you have a lot of load, you will just automatically add read replicas as you need. All the read replicas are attached to the same storage volume as the primary master. They're all available as failover targets for the master. You can have up to 15 of them across your 3 AZs. Typically, the Aurora replicas use log processing, redo log processing to update their caches. You don't have to update the storage volumes, right, because it's one storage volume. But you do have caches that are different in each of them. And you just want to make sure that if I get a redo record, if either it's in my cache or it's not, if it's not, I just throw it away. If it is inside my cache, then I need to update it. And I'm focusing on data caches, but there are also lots of other caches in MySQL and any other database, metadata, et cetera. So you have to deal with all of that. Generally, we found that our replication lag in Aurora tends to be in the 10 millisecond kind of range. And that's just, I see somebody laughing here because I'm sure he's used to MySQL bin log replication. It can be a bit longer. And you can imagine that with, if you're doing 200,000 writes per second, you'd be waiting a long, long time. So, I think that that's pretty cool with a load-balanced reader endpoint that does load balancing across these things and auto-scaling. And so then, you can just write and it'll automatically go to the one you need to. Last reInvent, I talked about online DDL, where, if you're familiar with MySQL, it does do, so to speak, online DDL, but what it's doing underneath the covers is a full table copy in the background. It rebuilds all the indices. It can take a long time. And then basically the DML is going into a new table that basically gets copied into, that needs to get reapplied after you do the switchover. And while you're doing that switchover, there's a table lock, right? And so it's kind of slow. So what we do is something very similar to redo logging, just schema logging. And so we introduced a new dictionary table where we do something like, here's the table, table 1, we're doing an operation, add column, this is the column name, and this is when we did it. And then we're done. And then we get, and it's got a timestamp against it. When we inspect a page, we have to say, like, okay, is there a metadata change that's happened to this page? And if there has been, we need to go and update it, right? And it's basically a modify on write, similar to the copy on write thing I was talking about earlier with cloning. Last year, we added support for adding a nullable column at the end of the table. In the next few weeks, we'll add a column anywhere and with or without a default. And so that, I think, should be useful to a lot of people. There are a lot of other, DDL operations that we should support. It's gone a little bit slower than I'd have liked, but, we'll do it. And if you look at the numbers, I mean, it's ridiculous. I mean, you can see that 5.7 is a ton faster than 5.6 in this regard. So if you're using 5.6, you should really think about 5.7. But, it's like many orders of magnitude different, right? And it just doesn't make any sense, how different the approach is. So one of the, we've often focused, in general, we focused on throughput for Aurora, like how many transactions per second can you push through the system, or how many selects can you push through the system. Sometimes we get people saying like, hey, I didn't get that 5x you promised, and we'll go and look at it, and it turns out that they're running one thread of sequential, select statements, or one thread of consecutive insert statements, and it's kind of hard to speed those things up, right? Because there's just a basic amount of work, and we can't do any of our tricks with throughput processing, asynchrony, and batching, and all of that stuff to make stuff faster if you've only given me one unit of work to go do at a time. But that doesn't mean it's not a legitimate thing to go speed those things up. And so here's a set of things that we've been doing for a single query or single operation performance, and most of this is. So asynchronous key prefetch. So one of the challenges we had in Aurora is that if you're using standard MySQL, you're going to make an I/O request through the Linux kernel, and it's going to try to recognize whether those I/Os are happening in sequence. And if those I/Os it thinks are happening in sequence, it'll start to prefetch blocks in. And so that's cool if your database is laid out that way. And it often starts out in a benchmark laid out that way, but then the way B trees work, you end up with random access patterns, and so it doesn't work super well. And so what we're doing now is that we basically look at the B-tree pattern, decide dynamically whether you're likely to be accessing a lot more blocks, and then pick the blocks you need to access. And we're doing network calls, not I/O calls, and we just start to load those into memory. And so this is the latency improvement factor versus what current MySQL batch key access joins using basically this is TPCH, slight variations. TPCH has got very formal rules, so this is basically the same queries and data, but not TPCH formally, running on R38XL. And you can see that at least on a cold data set, we're getting anywhere from no improvement to 4x to 10x to 14x, and so there are cases where it matters, and these are all against cold buffers. And so if you're running against a cached workload, this obviously prefetch isn't going to help at all, right? But if you are running a large query that has to do a scan, it's a pretty big deal. Speaking of batch scans, after you get the IOs in, the way MySQL works, error on the slide, is that you do a bunch of calls that are row at a time. Repeated function calls, locking, latching, cursor stores, format changes from InnoDB to MySQL formats. There's just a ton of work. And so we've started moving to a batch format for table scans, index range scans. And it's been worth about anywhere from, for the queries where that matters, it's been worth somewhere between 50 to 100%. So that's pretty cool as well. Hash joins. So any reasonable database should have hash joins. So we've added those, or coming soon. Again, on TPCH, you're seeing pretty significant improvements on the subset of queries where it makes sense to use that relative to batched key access. And if you're not familiar with hash joins, the basic idea is that you have two sides to a join, one which you're first, I should say. A join is where you're saying like something like A equals B, and you in one table and another, emp.dist, emp_no equals dep.depno or whatever. And what you do in this case is that you build a hash table on the smaller side, you ship it over to the other side, and you probe the hash table to find matches. It's a pretty standard approach. And so those are basically a completion of some of the near-term improvements that are happening. You can see that we're sort of trying to advance towards dealing with larger queries and so forth, and so forth. So serverless. So serverless is kind of an odd thing to try to think about from a database perspective, right? Because you can say like, okay, I've got some Lambda function. I'd just like to run a request. I'm willing to eat some latency. That's fine. And in that context, a request-based serverless system makes sense. But what about a system which actually benefits from having a warm buffer cache, and where you want to run, a few thousand, a few 100,000 requests per second? Now, you might still want that to be serverless to get the advantage of scale up, scale down. You might have variable workloads. You might have cyclical workloads. You might have unpredictable workloads. You might just not want to deal with the workload, right? And so, there are lots of, I would say the large majority of databases, 80, 90%, are not things that have a consistent level of traffic that's always on all the time. And for those things, it maybe makes sense to shut them down when not in use. For those things, it maybe makes sense to go and say like, oh, it's spiking usage, and I want to, rather than brown out or build a queue, I want to actually just make my database bigger or smaller, right? So that's basically what we're building here. So the idea here is that it starts up on demand, meaning a query hits it, SQL request hits it, it shuts down when not in use, it scales up and down automatically based on whether you're out of memory or CPU or whatever. Interestingly, no application impact when scaling. And it's pay per second, 1 minute minimum. And so what you see in this picture is your very familiar application, a database endpoint, basically an IP address. Underneath the covers, a request router that will have We'll touch on that a little bit. And then scalable database capacity. So you'll have one database node, but it's going to either grow or shrink based on a warm pool of instances that we manage. And obviously you have a database volume, the same 6 copies, all the rest of it, that's there all the time, right? You don't want to, just because you want the database instance to go down doesn't mean you want your data to go away, right? So what happens when you provision an instance? So what we do is that we give you a VPC endpoint, right? We give you an endpoint in each of your 3 VPCs, and it's connected to an IP address. And we set up a network load balancer, and we create a storage volume. And that's basically it. We don't create the database instance until the first request arrives. So the first request triggers the instance provisioning. Because of the warm pool, that typically takes, I think that slide may be wrong, it's typically around 3 to 5 seconds, which is pretty decent, right? And then when it'll scale up and down as your workload changes. Again, that's usually 1 to 3 seconds. And the instances hibernate after a user-defined period of inactivity. And the scaling operations are transparent. Why is scaling up and down transparent? It's because inside the request layer, we maintain your session state. And so we'll go and bring up another instance. Let's say you need to scale up. And then we'll find a point when you don't have a request active right now. And then we'll transfer the sessions over to the new location. Okay? And of course, the database storage is persistent until explicitly you delete it. And so what you basically specify in a serverless instance is this is the minimum size I want, this is the maximum size I want, and this is how long I want to wait before I hibernate this database, right? And so you can do something, like that looks a lot like existing Aurora by saying, oh, I want an R4, 2XL, minimum, maximum, never hibernate, right? That's basically the server version of serverless, right? We'll spin it up and we won't shut it down. Or you can say, look, I want it to go anywhere from a T2 small all the way up to an R4 16XL, and I want to shut it down after half an hour, right? And so that's useful. You can use that for dev test instances. You can use that in your CI/CD pipelines, right? Because someone makes a change to the application, you want to run a bunch of tests. Pretty much always that involves using a database, right? You could have cloned your database and have it run off of that. And so all of those sorts of things are valid, as well as things like, I have a game, the games have unpredictable workload. I don't want to deal with it. Just go and have it go up and down. Have games that have become less popular, but then eventually become, maybe through some old reference in some movie, become suddenly more popular. So you can't predict those things. And then you also have cyclical apps, right? Like I'm responsible for performance reviews as a manager, right, at Amazon. So the HR team is always using our performance management application. Twice a year, every manager is suddenly storming onto that system, and it's freaking slow, right? And during that time, it would be nice if it just could scale up and for those periods without anyone dealing with it, right? And I'm sure you all have those sorts of applications as well. It's actually the majority use case by far. So that's what I've got on serverless. Let me go a little bit fast through multi-master. So multi-master, so there really have been 2 approaches to dealing with multi-master problems in the relational database world. The first one is shared disk. And so what you do in shared disk is you say every instance of the database can access the common storage, and what you do is you fuse the caches together. So all the data, all the data is available to all nodes, and it makes it really easy to build an app, right? Because you can just send any request anywhere, and it's basically the same kind of cache coherency protocol as you might be, familiar with in running multi-socket multiprocessors on a motherboard, and and what the system is doing underneath the covers, it's making sure that if somebody's writing, that nobody else has that thing dirty and is writing, you have to get it from memory, or you have to get it shipped from the other socket, or if somebody is reading, then they need to, if somebody else has it dirty, then they need to move from dirty to read only, and then I have to get that copy, all of that kind of traffic. So the cache coherence traffic is pretty much on a per lock basis. And so if you're running a 2-node cluster, half the time, your typical data item will be local, half the time it'll be remote, and you'll be running a lot of traffic for those. The networking can be expensive. Typically these systems don't have a lot of nodes in them, and the nodes that tend to be close together, right, and running, sophisticated stuff like InfiniBand and so forth. And if you have a hot block, it's very similar to running, high-end system software on the multiprocessor. You end up having a lot of cache heat and things pinging back and forth in negative scale. Okay? So that's one model. It's very popular in the broader world. Oracle RAC looks a lot like this. The other model is to do a shared nothing system, where the application can continue to write to any one of these nodes, and the database takes responsibility for sharding the data across a multitude of data ranges, and then basically distributing the SQL statement and then converging it back. So the linkage here is in the SQL tier. So there's a lot less coherence traffic here. It's really just for commits. So because you need to make sure that if I wrote this piece of data, you wrote that piece of data, and somebody else did the opposite, that doesn't matter. So that means that you can scale to a lot of nodes. The problem here is that two-phase commit, Paxos commits are very heavyweight. The membership change algorithms are very heavyweight. Since it's range partitioning, you typically end up with you can easily end up with hot partitions because it's not just a hot block. Now I'm doing something at a partition level. So let's say I partition the obvious way by date range so that because most of my queries were by date, it's very likely that the inserts are all happening into the last partition, right? And cross-partition operations become expensive. So these systems are much better at small requests. You see it very commonly in systems that I would categorize as NoSQL, right? And like Cassandra looks a fair bit like this, I would say. We're doing something different. So it's a complicated page, sorry about that. And so what we sort of say is that, there are oases of consistency in Aurora. And so like the head node knows exactly what order each transaction in that data, its node should be. Another head node, same thing. Any given storage volume knows the partial order of writes that it received and must be satisfied, right? And so if you believe that, then if you can know those two things, then the only time that you could possibly have a conflict is, given that all of these guys have observable individual state, is when data has changed both at multiple database nodes and at multiple storage nodes, right? So if two guys are writing to the same storage volume, it's ordered, and that's fine. If the same guy is writing to two storage volumes, well, that's just regular old Aurora. That's totally fine, right? And so since there's we're doing conflict resolution here, there's much less coordination that's required. And what we do is that when there is coordination, it's basically hierarchically managed through a ledger. And like this is a case where the blue guy is writing to page 1, then page 2, and the orange guy is writing to page 2 and the page 1, and one write succeeded on page 1 and the other one succeeded on page 2, and so wait a second, now I'm not able to achieve something. And so both of these, the storage node is aware that it received something that it couldn't satisfy, and so it can't be satisfied at an individual storage node, it can't be satisfied at an individual head node. So what we have done is we elect a leader, an Ubermaster, if you will, and one of its responsibilities is to manage a ledger. And all a ledger is a fancy word for effectively a redo log by a different name, a different kind of redo log. But and it's responsible for saying, okay, who's the victim, right? And so the idea here is to, and that's very similar to like dealing with lock conflicts in a traditional lock manager and picking a victim when you have the deadlock. And so you just basically have to do that. The cool thing about this is that you can make it hierarchical. So in some sense, the database and the storage node are providing the base level of ordering. The Ubermaster is providing the next level of ordering. And you could imagine that if you were building multi-master, multi-region, then if you have regional conflicts where something is writing across multiple regions, then you can just basically elect a Ubermaster, across regions as well, right? Let's quickly look at crash recovery here. So crash recovery, we discussed what single master looks like. Multi-master is actually more complicated, and then that's because losing one database node doesn't mean the other one's gone, right? So in this case, you've got, again, the blue guy and the orange guy. The blue guy went away. So here we just need to go and make sure, they each individually have a volume complete LSN. They each individually have a completion point thing. And so you have to do that same ragged trim that I talked about earlier, but just for one of the nodes. And so, that has implications on how we record LSNs, and transaction IDs and all the rest of it. They have to contain the head node ID. Multi-master, multi-region multi-master is basically that same protocol. What we do is we are doing that same replication thing that I talked about within regions, which is physical replication using redo logs. We ship it across regions. So that'll actually be pretty cool. It's actually a separable feature. We should be launching that in Q1 sometime. And that gives you cross-region physical replication in something under 10 seconds, I would think, because you're mostly gated there by the physical distance of the wire. And that's, again, I think a pretty cool thing. In the case of doing that with multi-master, what you're basically doing is I have a local partition, you have a remote partition, and I have to do the same kind of thing that I do in a shared nothing system about deciding where to send the writes and doing two-phase commit or doing a ledger. Right? So this is something that didn't make the cut for the keynote, but I think is a big deal. So parallel query processing for Aurora. So wouldn't it be, if we've got thousands of CPUs in the storage nodes, wouldn't it be cool if I could use those to do queries? And I've got the data, right? Why the heck not? Exadata does something like this. And so why wouldn't I be push down and parallelize my query processing across these thousands of nodes using the storage fleet? And moving the processing also reduces network latency, right? And traffic, which is important if that's my key concern. Some of the challenges I face here is that the data storage we store in the storage node is not range partitioned because we want to avoid heat. So you need to do full table scans for this operation to work. Data may also be in flight, right? You have these read views and so forth about what data I'm allowed to see, what data is committed, et cetera. And you may not be allowed to see all of the data, and not all functions can be pushed down. Okay, so so what we basically do here is that we produce a plan, we create a context, we send it down. The storage node is responsible for streaming stable rows back up, as well as a raw stream of unprocessed rows, so the head node can do its magic with undo processing to get the version of the data it's allowed to see, and then it combines that to do the final result. So that's basically an overall view. From a storage node perspective, we run 16 parallel query processes on each node, each one associated with an individual query. And what it gets is, here's the list of pages I need you to scan, here's the read view and the projections, here's the expression that you need to go and run on that code. And we do two passes, one to do filter evaluation, one to do expression evaluation. And then we send the data back. So here's an example of a parallel hash join where we're basically pulling the data. We run a Bloom filter to pick out the values that are interesting, push it back up. And it's a fair bit faster. So it's so that's point query on the non-indexed column is basically a scan. An aggregate query is a scan followed by an ag, and an ag plus two table join. So you get advantages, right? And that's just because we're able to operate on the resources want. So I can take questions for just about 5 minutes, and I'd be happy to answer more questions outside the room after that. There are two mics over there on both at the two spots if you want to ask any questions. Sorry, I had to run really fast through the end of this presentation.
Hey, question here. When are you planning on having Aurora available in all regions?
So right now, it is available in all of the regions that have 3AZs except for Brazil. And basically, as soon as we get available capacity in any 3AZ region, you can expect Aurora to be there. People have, we've gone and added AZs to regions like Frankfurt, for example, in order to support things like us and EFS and things of that nature. But we have every desire to go to 3AZ pretty much anywhere that we have a region. And when we do so, you can expect that Aurora will be there.
How much of this will apply to Aurora Postgres?
So everything that is storage-based basically applies pretty quickly and immediately. Things like the volume cloning and so forth. Things that require some database work will take a little bit longer, right? And right now, I mean, Aurora Postgres really just went out a few weeks ago. I think the way I tend to favor doing those things is that usually you want to let things quiesce, take customer load, deal with your tickets, and just sort of deal with like the things that customers really want that you maybe didn't quite get the fit and finish quite right before you start to add on. And there is a bunch of stuff that we need to add in Aurora Postgres, Lambda functions, load from S3, all that kind of stuff. We'll get there, for sure. Right?
Is it possible to launch clones from CloudFormation?
So it's just an API call, so I think you should be able to do so. I'm not really familiar with CloudFormation, but as long as you can make an AWS API call, you should be fine.
About this multi-master thing, we're dealing with the write confliction, so we don't have to dealing with the read and write confliction anymore, or do we still need to?
I didn't quite understand the question. Could you repeat it?
Yeah, basically we are saying if we have multiple writer, right, if they get conflict with a certain page, we have to deal with that. But for the read part, we talk about that cache coherence stuff, right? If you read and if you read a very old version, you have dealing with that, or we don't need to do?
Yeah, so I think the basic point you're making is that if you have a multi-master configuration with reads and writes, you don't really need read replicas anymore. And I think that's fair, yeah.
No, my point is you have multiple masters, and one master is read some page in its memory, but it's a very old version. Do we need to handle that?
Okay, that's correct. So we have to deal with that, right? And so, there's heart beating going on all the time. There's fuzz about what read view you're allowed to see, and all of those sorts of things. So yes, it definitely has to present the image of a single database, which really has to do with the same sort of Lamport clock mechanisms, the same sort of time-based notions of how up-to-date you can afford to be as anybody else. You have to have an understanding of what data you read last or wrote last in your individual request to decide what is readable in your next request. So there's a whole bunch of that kind of work, of course.
Thank you.
Hey, I might have missed this update, but is there any updates on 5.7 support?
Yeah, it should be out within the next month.
Thanks.
Any chance that at some point in the future we might get to have a Postgres read replica from a MySQL variant master?
Oh, wow. I have not received that request before.
Take my money.
Yeah, I'll think about that. Maybe you can show up afterwards and get a card, and you can send me an email with the use case in some detail.
With the serverless, will it just increase the size of the Aurora instance, or will it actually spawn multiple masters or whatever you need?
So right now we grow and shrink. We are not in an initial release contemplating doing read replicas or multi-master or any of those sorts of things. My sense is that multi-master and read replicas and multi-AZ and all of those sorts of things are generally more applicable to always-on systems. I do think that if your intuition is that, hey, why don't those guys want things to scale up and scale down? I think that's a legit point. I need a bit more experience with both of those features before I attempt to combine them. Okay, I think that's everything. I'm just going to unmic, and then I'll be outside if anyone has any other questions. All right, thank you, guys.